is one major source, as methane gas trapped within the layers of oil or coal often ends up being released. Livestock farming emits similarly large quantities. Amazingly, cows burp methane when bacteria break down the grass in their stomachs. The bacteria that break down the animal waste also have a similar effect. Livestock farming produces methane in far higher quantities than animals in the natural world. Another farming practice that's a major methane producer is rice cultivation. Here it comes from the bacteria in paddy fields. Methane is also generated in significant quantities from discarded organic matter as it's broken down in landfills. Reducing our dependence on fossil fuels, as well as the quantity of meat we consume, and buying locally to reduce the footprint, are among the obvious ways to reduce methane emissions. But there are also other techniques being developed. Leaks can be reduced in fossil fuel production, or the gas can be stored for fuel rather than being vented off into the atmosphere. Improvements can be made in how we dispose of our organic matter. Changes in animal feed and other methods can reduce livestock's methane output too. All of these ideas and more will be needed if we're to significantly lower the amount of methane in the atmosphere. In the summers of 1936 and 1938, a small scout plane flew over the Arctic islands of Svalbard, photographing the terrain. The people on board had no idea how important the images they were capturing would be in demonstrating some of the most extreme effects of climate change anywhere in the world. To them, this was just a routine survey to create a map. They didn't know that much of the ancient glacial ice that they were flying over would soon be gone forever. For many years, the photographs sat in a drawer, forgotten. It was only 80 years later that they were rediscovered, and it was realized they contained enough detail for software to reconstruct the area as an accurate 3D model. This could then be compared directly with how the same area looks today. In front of you is a small part of that model. You can compare the 1930s reconstruction with how the same area looks now. The red areas highlight how much ice has melted away. From this comparison, we now know exactly how much the glaciers of Svalbard have declined, and this chart shows the result for the whole area. The blue shows where the ice has increased, and the red where it's decreased. For at least the past 150 years, most glaciers on the planet have been slowly shrinking. But in the last 40 years, the rate of melting has dramatically accelerated. Recent findings show that now almost all of the world's glaciers are retreating simultaneously, which hasn't happened for at least 2,000 years. Summer is the crucial time for glaciers. Most of the damage is caused by longer, warmer summers, melting more ice than's being replaced by fresh winter snowfall. Polar amplification has increased the rate of warming in Arctic areas. Svalbard is particularly vulnerable because there the rate is even faster, but many other areas are also badly affected. In just the last 40 years, the average thickness of the world's glaciers has reduced by 24 meters, the height of an 8-story building. In that time, an incredible third of the volume of New Zealand's glaciers has melted away. Since 1901, melting glacial ice has been a larger contributor to sea level rise than the ice sheets of Greenland or the Antarctic. If we lost all the world's glaciers, that alone would cause a global sea level rise of 0.5 meter. Even now, devastating flash floods can occur when melting walls of glacial lakes burst, creating a deadly wall of water that can engulf villages downstream. The loss of glacial ice removes a key source of seasonal meltwater that supplies fresh water for important wildlife habitats. We rely on this water too, for drinking and many commercial activities. Unfortunately, every future scenario shows that glacial retreat will continue. But reducing the global rise in temperature will help to reduce the rate of decline. This would have a big impact on the amount of global sea level rise. Whatever happens, photography will continue to play a vital role in documenting what was once there. "68% of the fresh water on Earth is stored in two giant ice sheets, thousands of meters thick, covering most of the surface of Greenland and Antarctica. These were formed from snow, becoming compressed over many centuries under the remains of the last ice age, a time when ice sheets covered much of northern Europe and North America. Over time, the ice, moving under its own weight, gradually flows towards the coast. This eventually forms ice shelves that float on the ocean. These in turn carve into icebergs and melt away in the relatively warmer oceans. New snowfall helps to replace the ice, but is this sufficient to prevent the ice sheet flowing away? Measuring the overall gains and losses is important because when the water from the melting land-based ice finds its way to the ocean, it contributes to a rise in sea level. Accurate measurements taken using satellites have found that the amount of ice is steadily declining, particularly in Greenland and western Antarctica. As an ice sheet melts, its height reduces, which exposes the surface to higher temperatures at lower altitudes, causing yet more melting. This reduces the level even further in a vicious circle. Currently, this could be stopped if we halted the rise in global temperatures, but that may not always be the case. If this continues, it could lead to an irreversible decline, a climate tipping point. It is thought that for some parts of the ice sheets, this could occur soon with our current rate of warming. Preventing global sea level rise would then become an even greater challenge. Welcome to Climate Station. Using interactive gaming technology, we can explore how our planet's climate works, see how it's changing, and what could happen in the future. Let's start in 1901 and run through the years to the present day. The pins show the difference in temperature relative to the middle of the 20th century. Blue pins are cooler, red pins are warmer. The longer the pins, the greater the difference. Watch how the cooler blue areas gradually disappear, and then the warmer red pins take over as the planet warms up. You can see how the warming has accelerated, particularly in recent years, and some areas have warmed more than others, especially the Arctic. We can select any point on the planet to go into more detail, so let's pick a location in the Arctic, Svalbard. The graph on the right shows that if you happen to live there, you'll have seen the temperature rise by over 3 degrees since the middle of the 20th century, and this has had a dramatic effect on the glaciers there. Using photogrammetry from an aerial survey in the 1930s, for the first time, we can see exactly how much ice coverage has been lost from this vast 500 square kilometre area. This shows how the glaciers were in 1936. And this is what they're like now. The red areas highlight how much ice has melted away. The melted water flows into the ocean and contributes to global sea level rise. This graph shows how much the level has risen over time. It's increased by 7 centimeters in just the last 20 years. We can also explore many other important indicators of climate change. We can look at the rise in atmospheric CO2 compared with the global temperature. Advances in technology allow us to build up a more complete picture. Since the 1950s, we've been able to track the rise in ocean heat. More recently, satellites have allowed us to measure the amount of sea ice and the loss of ice sheets in Greenland and Antarctica. We know we must cut our greenhouse gas emissions to solve this problem. But what are the expected consequences of climate change? Let's look into where we're heading. IPCC climate models show us a range of possible outcomes. This is one of these projections, what's called the medium scenario, where we're currently heading and our best estimate for the end of this century. Based on current rates of greenhouse gas accumulation, global temperatures will continue to rise and the world will become a very different place. By 2100, we will reach 2.8 degrees of warming, a long way from our 1.5 degree target. Heat waves, droughts, and heavy precipitation will become more frequent and intense. Tropical cyclones are more likely to generate devastation on the scale of Hurricane Dorian, as shown here. The consequences will affect everyone. But it doesn't have to be like this. We've already come a long way and rapidly adopted green energy technologies. About 15 years ago, climate research indicated 4 to 5 degrees of warming was possible by 2100. So, let's switch to the IPCC's very low scenario, where we act fast and at scale, lowering our emissions to net zero by 2050. As you can see, we can still keep 1.5 alive and avoid the very worst effects of climate change. This requires a change in every part of our economy and society. A drastic reduction in emissions from transport, buildings, industry, agriculture, and energy production. We need to go further and faster and to commit to action. Together, we can safeguard our future. All life on Earth is part of an intricate web of species that rely on each other for survival. If any are threatened, it risks upsetting the balance, potentially also threatening our survival. Yet it's thought that 1 million species currently face extinction. Species are becoming extinct 100 times faster than in pre-human times. In the last 50 years, the thousands of populations monitored by the World Wildlife Fund have declined on average by over 69%. If this decline continues, it will have a dramatic effect on us, with loss of livelihoods and threatened food supplies. So, is the current loss of biodiversity caused by climate change? Well, actually, the majority is caused by natural habitats being destroyed by changes in land use. But biodiversity and climate change are very closely linked. Deforestation, for example, reduces both biodiversity and the ability of the planet to absorb carbon dioxide from the atmosphere, leading to rising temperatures. These rising temperatures can lead to further biodiversity loss. A good example of this is what is currently happening to coral reefs in many parts of the world. Coral reefs are the foundation of unique ecosystems, home to many types of marine life. Corals are marine animals, similar to sea anemones and jellyfish. But unlike them, they secrete hard calcium carbonate exoskeletons that, over many years, grow into giant reefs. The biggest collection is the Great Barrier Reef in Australia, which is the largest structure made by living organisms. Corals typically feed off microscopic plants called algae that in turn need the corals to survive. It's the algae that give the corals their vibrant colours. In front of you is a life-size replica of a real coral reef, made using advanced photo-scanning techniques. Some of the corals are brightly coloured as normal, but many here have lost their colours altogether. They are victims of what is known as coral bleaching. Rising ocean temperatures cause the algae to release toxins, and the corals have reacted by expelling them. With the algae gone, the corals turn white and often die, threatening the ecosystems that rely on them. Recently, bleaching events have become increasingly common, and corals have died on a massive scale in many parts of the world. The reef here was a victim of a major mass bleaching event in 2016. The scan used to create this model was taken in 2022. Some of the flat table corals are now regrowing, but it's thought the next time a similar event happens, they'll be wiped out completely. Reefs recover, but it can take many years and will happen only if water temperatures allow. As the planet warms, an increasing number of ecosystems are likely to become threatened. The more rapid the warming is, the less likely it is that nature will be able to adapt. If that warming goes beyond 1.5 degrees Celsius, it's thought that climate change will become the biggest contributor to biodiversity loss. When the climate in a location changes significantly, it can force its inhabitants to move elsewhere. This is particularly true for countries that can't afford to adapt to the new conditions. Recent sea level rise has caused the soil in low-lying areas to become salty, threatening the survival of any crops growing there. Other areas are in danger of becoming submerged altogether. Flooding is a threat that not only affects agriculture, but can impact urban areas too, particularly those located in coastal areas. At a rough estimate, more than 200 million people worldwide live along coastlines less than 5 meters above sea level. But by the end of the 21st century, this figure is estimated to increase to between 400 and 500 million. We're also seeing an increase in higher temperatures and drier weather, which can lead to long-term drought, another major agricultural threat that can force people to move elsewhere. But climate migration is nothing new. In the 1930s, the Dust Bowl in the southern plains of the US caused millions of people to face starvation. They were forced to move towards the west, rebuilding their lives in new locations, such as California. The problem had been triggered when farmers mistakenly removed deep-rooted grasses, not realizing they're vital for keeping topsoil in place. Years of prolonged drought and high winds then caused the topsoil to blow away, making the land uninhabitable. Unfortunately, current climate change is likely to have an even greater effect. A UN report states that there were nearly 10 million weather-related displacements during the first half of 2020 alone. The World Bank predicts that by 2050, there could be double the number of climate migrants as refugees in the world today. Fire is an important and natural part of life on Earth, and some plants actually rely on it for their survival. It limits the growth of competing species, and its heat releases their seeds. But it can take years for nature to recover from a wildfire. As the planet warms and humans alter the land, wildfires are becoming increasingly frequent, more intense, and now spreading to regions where previously they were rare or unseen. Hot, dry, windy conditions make vegetation vulnerable to combustion and help the fires spread. Fires which are often started by human activity. A discarded smouldering cigarette or a lightning strike is all that's required to start a fire that will burn through a vast area of land. Trees store carbon as they live and grow, but release massive quantities of it into the atmosphere as they burn, contributing to the very warming that will encourage yet more fires in the future. A damaging, vicious circle. It's important that forests grow back as quickly as possible. Forests are often called the lungs of the planet because they help to maintain the Earth's balance of carbon dioxide and oxygen. Actually, oceans play the biggest part of all, but even so, forests absorb approximately 30% of our carbon dioxide emissions. As trees harness energy from sunlight, they not only extract carbon dioxide, but also release oxygen into the atmosphere. Like wetlands, forests also help to maintain the balance of water in the atmosphere and ground. Trees can draw water from underground through their roots, releasing it into the atmosphere through their leaves. Without this, areas become drier, and this can prevent forests from regrowing again. A vicious circle. Also, without forests, rainwater doesn't soak into the soil as effectively. Instead, it runs directly into rivers, which can make flooding more likely. Despite the importance of forests, humans have so far removed a third of them to clear land, mainly for agriculture. Over thousands of years, most of the forests of Europe, North America, and parts of Asia have been destroyed, but in the last couple of centuries, the rate has increased, hitting a peak in the 1980s. Most deforestation now occurs in tropical rainforests, which is a major threat to nature's biodiversity. In 2019 alone, an area roughly the size of a football pitch was lost every 6 seconds. This extensive deforestation changes the local climate by both reducing local rainfall and increasing the chances of flooding. It also contributes to global climate change by reducing the amount of carbon dioxide being absorbed from the atmosphere. Globally, the more new trees that can be planted, the more this reduces the problem. Forests have an enormous environmental importance, but despite being much less well known, peatlands are important too. In addition to filtering drinking water for millions of people, they store up to twice as much carbon as all the world's forests combined. But when peatlands are drained or disturbed, their carbon is released back into the atmosphere. This contributes close to 5% of human-caused greenhouse gas emissions. And when the dried peat catches fire, the amount of carbon dioxide released can double. So, what is peat, and why are peatlands being destroyed? Peat is a type of soil formed when low oxygen, waterlogged conditions prevent dead plants from decomposing properly, preserving them like pickles in a jar. The plant's carbon is trapped within the soil, preventing it from returning to the atmosphere. Peatlands cover around 3% of the Earth's land surface and are found in almost every country. But since 1970, 35% of the world's peatlands have been destroyed. For centuries, people have been draining peatlands and extracting the peat to use as a fuel and for improving plant growth. Until recently, most people were completely unaware how much this damages the environment, with some serious side effects on people's health and well-being. When water's drained from peatlands, the peat soil starts to react with the air, releasing the carbon that's been captured and stored for centuries. The dried out peat becomes vulnerable to burning. Any ignition source will easily set it on fire. Since the layers of soil in peatlands can be very deep, fully extinguishing fires can be extremely difficult. In Arctic regions, peatlands are known to burn under the snow, undetected for months. Southeast Asia is also particularly affected by these fires, especially in the dry conditions enhanced by El Niño. In that part of the world, large areas have been cleared for agriculture, such as palm oil plantations. Cloud cover can make the true extent of these fires difficult to spot, but improved satellite monitoring now gives a more accurate picture. Recent estimates for the quantity of carbon dioxide released from these fires is astonishing. On some days, it's comparable to the amount released by the whole of Western Europe, China, or the United States over the same period of time. The smoke from the fires is a major health hazard and is thought to have caused many premature deaths. It seems obvious that restoring peatlands should be a priority, but there's a catch. Wetland areas contain bacteria that emit large quantities of methane, a greenhouse gas far more potent than carbon dioxide. Even so, methane stays in the atmosphere for a much shorter time, so in the long term, the reduction in carbon dioxide more than compensates for the increase in methane. Carefully managing water levels and the type of vegetation that grows there can greatly reduce this issue as well. Recently, initiatives have been put in place across the planet to restore large areas of peatland and prevent further damage. This should help to protect the natural world and combat climate change. Geological research using rock and ice cores shows that the Earth's average sea level has risen by over 125 meters since the middle of the last ice age, about 20,000 years ago. Sea levels have stayed almost the same for the last 8,000 years, though. But just over a century ago, they started to rise again. They have risen by over 7 centimeters in just the last 20 years alone, the same amount they increased over the previous 60 years. We've been measuring sea levels accurately with tide gauges since the 1600s, and now satellites provide far more coverage. They show that some regions have experienced a greater rise than others. In Europe and the east coast of North America, levels have risen over 3 times more than the global average. Sea level rise has a number of significant causes. For example, melting glaciers and land-based ice sheets, and the volume of oceans expanding as they've heated up. The latter occurs from a process called thermal expansion. Over time, this heat is released into the atmosphere. This means that the melting ice sheets are likely to be the main contributing factor to sea level rise in the future. Sea ice is melting too, but like an ice cube melting in a drink, it barely affects the level. Although the recent rise can be measured in centimeters, rather than the meters of the distant past, it is already having an impact on low-lying coastal regions. This will be felt elsewhere in the future. Predicting sea level rise is complex, but the last time Earth's global temperature was similar to today, 125,000 years ago, the sea was at least 5 meters higher than its current level. Could this happen again as the full effects of climate change pan out? How high the sea level rises depends on how much the Earth warms. The future projections give us our best estimate of what is likely to happen this century. Floods can play an important part in the natural world, but they can be very disruptive and dangerous. So, is climate change making them worse? Before we answer this, firstly we need to look at the different types of floods. Some are caused directly by human activity, such as badly designed urban developments or poor water management. For many areas, however, the effects of a changing climate pose the most serious threat. It's well known that as the planet warms, snow and ice melts, and sea levels are expected to rise. By the end of the century, over 400 million people are predicted to be living in areas less than 2 meters above sea level. This makes them very vulnerable to coastal flooding. The most severe form of flooding is caused by storm surges. But what are they, and why are they so dangerous? They occur when storms create strong winds over the ocean, forcing the water to build up. High tides and the low pressure of storms can make them even worse. This is what happened, for example, in 1953, when severe floods occurred around the North Sea, affecting the Netherlands, Belgium, and the UK. The most extreme storm surges generated by tropical cyclones, when sea levels can sometimes rise many meters in just a few hours. It's not surprising they've caused some of the worst natural disasters ever recorded. For example, flooding in the Ganges Delta in South Asia by the Bola cyclone in 1970 killed hundreds of thousands of people. Unfortunately, climate change is likely to make storm surges worse. As the surface of the oceans warm, these storms can pack an even more powerful punch. This, combined with the rising sea levels, will increase the severity of storm surge flooding in the future. But it's not just storm surges that pose a threat. Extreme rainfall is another major cause of flooding. In fact, in 1931, it led to the deadliest disaster of the 20th century, when prolonged rainfall, combined with melting snow, overloaded the Yangtze River in Asia. The local soil and terrain conditions amplified the effect, flooding thousands of square kilometres of land. Other factors, such as a dam failure and cholera outbreaks, were also major contributors to the extensive loss of life. That flooding took months to build up, but sometimes intense rainfall from a single thunderstorm can cause flash floods. These can also be very dangerous, particularly when the water contains debris swept along by the flow. When floods lead to structural failures, the consequences can be greatly magnified, as was the case in 1979 with the Machu Dam in India. So, could rainfall events also be affected by climate change? Well, a warmer atmosphere stores more moisture, so unfortunately the answer is yes. Already, rainfall records are being broken more frequently. As the intensity of rainfall increases, the chance of severe flooding increases too. Warmer conditions can also generate flooding directly by increasing the amount of melting snow and ice. This can not only overload rivers, but also weaken the banks of glacial lakes, causing catastrophic structural collapse and devastating flash floods. This happened around Lake Palcacocha, South America, in 1941. The severity of flooding doesn't just depend on the quantity of water, but the conditions of the soil. In some regions, increased temperatures dry the soil, allowing the ground to soak up excess rainwater. In other regions, infrequent, intense downpours cause the soil to become hard and impermeable, which creates the opposite effect and increases the chance of floods. So, going back to our original question, is climate change making flooding worse? Well, the factors affecting flooding are complex, but it's predicted that when floods occur, they are increasingly likely to be more severe in the future. Thankfully, there are ways we can minimize the impacts. Flood protection and barriers can be very effective defenses and have been added in many areas, particularly along the coast. Advances in technology allow many of us to have better weather forecasts and warning systems that give us more time to prepare. In 2021, for example, rainfall on the Yangtze River was even greater than it had been in 1931, but thankfully the loss of life was far less. Hopefully, these can improve further still and become available to all parts of the world. In polar regions, the surface of the ocean is cold enough to freeze. The amount of this sea ice varies with seasons reaching a minimum in late summer. Satellites have been accurately monitoring the extent since 1978, and for the past 30 years, it's been dramatically declining in the Arctic. This is concerning because sea ice helps to regulate the planet's temperature. An ocean covered in bright white sea ice can reflect 80% of the sunlight that hits it back into space, whereas the dark ocean on its own can only reflect about 10%. The rest is absorbed by the ocean, causing it to warm. This in turn causes yet more ice to melt in a vicious circle. Many future projections show that by the end of the century, the Arctic Ocean could become completely ice-free in the summer. This may allow new trade routes to open up, though the effect on the rest of the planet would far outweigh any benefits. Entire ecosystems that currently rely on sea ice could be destroyed. Unlike the melting of land-based ice sheets and glaciers, melting sea ice would have little effect on sea level rise. This is similar to how a floating ice cube melting has little effect on the level in a glass of water. Around the Antarctic, the extent of sea ice has been much more stable than the Arctic for a variety of reasons, including how ocean circulation behaves in that area. Also, because there are no land masses near Antarctica, each year's ice can float away. Very little Antarctic ice remains all year round. During 2023, the levels of Antarctic sea ice were far lower than ever previously recorded. Have you ever wondered if climate change is affecting where you live? In the observations section of Climate Station, you can find out. You can select a location close to your home on the globe and look up all the temperature data. Let's say we wanted to look up the temperature for this location. We can select it on the globe, pick a recent year, and see the average temperatures for every month. But how does that differ from the temperatures in the past? We need something to compare against. We use what's called a reference climate. This is the average temperature over a 30-year period of time. We could choose any 30-year period as our reference, but Climate Station uses 1961 to 1990, a period often used by climate researchers that lies within the middle years of our dataset. On the globe, we can represent areas cooler than this climate with blue pins and warmer areas with red pins. The longer the pins are, the bigger the change is. For our chosen location, we can now plot a graph showing how temperatures differed from the reference climate over the years. But now let's compare it with what's been happening inside the Arctic Circle. In this part of the world, the change has been dramatic, particularly in recent years. But we can go one step further. We can compare what's been happening to the warmest summer months and the coolest winter months for each year. Let's select the warmest months. This graph suggests that the temperatures in summer haven't been rising quite as dramatically. Now let's have a look at the coolest months. The change is far more noticeable, indicating that not only are the overall temperatures rising, but the coolest months are getting warmer here more than the warmest months. On the globe so far, we've only been able to look at 1 year at a time. But if we take a 10-year average, we get a much better idea of the overall trend. Here are the 10 years from 1901 to 1910. Now let's jump to the last 10 years. Switching between the two, we can really see how much the climate has changed over the last 120 years, particularly in the Arctic regions.